So let's start with a really basic introduction to inverses. Okay, f of x is 2x plus 1. The domain is negative 4, 2, and 3. So what are the values of f here? Going back to Algebra 1. Or pre-algebra, if you will. Okay. So f of negative 4 would be negative 7. F of 2 would equal, what did we say, 5? And f of 3 would be 7. Okay? Now, what is the inverse then? Okay, it's not, that's the notation, is this little negative 1. Do not think of that as an exponent. Okay. How do we do inverses?
You just
Switch the x's and y's, okay? So, the f inverse, what is going to be, this is the domain of f, and the range of f ends up equaling negative 7, 5, 7, right?
Mm-hmm.
What's the domain of the inverse? Not f prime.
The domain would be negative 7, 5, 7.
Okay, yeah, look at this. I'll actually change colors here. If I'm doing the inverse, the domain is going to be what the range of f was. So this is the domain of f inverse. So I'm doing f negative 1, f inverse of negative 7, f inverse of 5, and f inverse of 7. What's f inverse of negative 7? Negative 4. F inverse of 5? 2. F inverse of 7? 3. So you see here that the range of the inverse is the domain of the original function. Okay, now these are things that you've learned in the past, but we always like to remind ourselves of this first. Okay? Now, that brings us to the definition of the inverse function. Okay, and here's a little illustration. But this definition is important because if you're told to prove that two functions are inverses of each other, then both of these have to be true. When you do f of g of x, you need to get x. And when you do g of f of x, you've got to get x. Okay? This is why the derivative and integral are not exactly inverses, because when you integrate, you get that plus c. It doesn't necessarily take you back exactly where you started. Okay? But an inverse will. And you can see here, I have in blue the domain of f and the range of f, and the function will take us from the domain over to the range, from the domain over to the range. But then we have this g of x. G of x is the inverse in this context. The inverse function will take this value from the range of f in its domain and take us right back to where we started for every point. Okay? So that's important to remember as we're looking through this, okay, and in our lessons to come. So, here, if I wanted to show that f and g are inverse functions of each other, the first thing that I need to do is I need to do f of g of x. Okay? So f of g of x, instead of 2x cubed minus 1, I've got 2 times g of x cubed minus 1. Okay, well, g of x is that cube root, so 2 times the cube root of x plus 1 over 2 cubed minus 1. The cube undoes the cube root, so now it's 2 times x plus 1 over 2 minus 1. Now we have the 2's canceling. So we have x plus 1 minus 1, which equals x. So that worked out the way it's supposed to. Okay? But that's not good enough to prove that they are inverses of each other. You also have to prove that g of f of x will equal x. So we're not doing the cube root of x plus 1 anymore. We're doing the cube root of f of x plus 1 over 2. So let's plug in what we've got. Okay, f of x was x cubed, 2x cubed, minus 1. Okay? Well, the minus 1 plus 1 cancel out, so now I have the cube root of 2x cubed over 2. The 2's can cancel. And I have the cube root of x cubed, which equals x. So, we've proven both of them, and we should then say, therefore, f of x and g of x are inverses of each other. Okay? Now, one thing to remember here, looking at the graph, is notice that two graphs, or the graph of a function and its inverse, will be a reflection across the line y equals x. Okay, so we had this line y equals x right here. And we have the function f of x, that's this one right here. Looks like it's got a plateau point there, and then it goes up. Okay. And then also we have this g of x, which was a cube root. And notice they intersect each other right on the line y equals x. Here, what was a plateau point on the function translates into a vertical tangent on the inverse, okay, because it's been reflected across. So a horizontal tangent becomes a vertical tangent, okay? So we have that symmetry there, that reflection, okay? Now, how do we know that a function has an inverse function? It's got to be 1 to 1. Okay? It's got to be 1 to 1. Now, what does 1 to 1 mean? Okay?
That for every x, there's only one y.
Okay, for every x, there's only one y. That's what makes it a function, right? If one x, like a here, got mapped to two different y's, that would not be a function by itself, okay? So what makes it a 1 to 1 function?
Every y has one x.
Yeah, there you go. Every y only has one x. So notice here, this y value right here, there are two different x values that give us that y value. So that would not be 1 to 1. And the reason why that means there's not an inverse function is, think about it. Remember, we said that a function and its inverse are reflections of each other across the line y equals x. Now, if I were to reflect this across the line y equals x, notice what it would look like. I would have something that looked like this. Whoa, not that. Is that a function? No. So, can we reflect a lot of stuff across the line y equals x? Yes. Does that mean it's an inverse? No. Okay? So, do be careful with that part. But in order for it to be an inverse function, we have to have a one-to-one function. And that's where we get this term we talked about a while ago. It's been a while since we've really talked about this term, but strictly monotonic. What does that mean again?
X for every y.
No?
It's like it doesn't have a point inflection.
It doesn't have a
Change
change in
second.
direction.
Concavity.
Okay? We could have a change in concavity, like you see here with the cubic one, we have a change in concavity, but we did not have a change in direction. It continued to increase over its entire domain. Okay? So we would call that strictly monotonic. There are no changes in direction. Okay? So, let's look at these. Which of these has an inverse function? Okay? Which of these has an inverse function? We could tell by quickly doing the derivative and trying to find critical points, right? So let's see, if I had f prime of x here, I'd have 3x squared plus 1. If I set that equal to 0, I'd get x squared equals a negative 1/3. So I have no critical points, or no critical values, which means I have no maxes or mins, no change in direction. Okay? No critical values means no max or min points, relative max or min points, so therefore no change in direction.
Did you have to find the second derivative to like verify that, or is that always true?
Well, the second derivative, remember we said it can change concavity, it just can't change, direction. Okay? So, this one does have an inverse. Okay? So, has an inverse. Because no change of directions means it is one-to-one. Now, on this other one, if we found the derivative, 3x squared minus 1, if we set it equal to 0, then x squared would be positive 1/3, and x would be plus or minus root 3 over 3. Okay? If we do a sign diagram for that, where we have a negative root 3 over 3, a positive root 3 over 3, if we did the sign diagram for that, we'd actually end up going positive, negative, positive. We see changes in direction. So there is no inverse. Okay? So changes direction, so f of x is not 1-to-1, meaning there is no inverse function. Okay? So that's a really quick, easy way that you can check to see if it will have it if you can't see the the graph. Now, how can we tell just by looking at it if there was an inverse? This is something that you looked at back in pre-calc. How can you tell if it's got an inverse function just by looking at it?
Horizontal line test.
Yeah, remember we had the vertical line test to see if it's a function? Well, if you reflect it across the line y equals x, then anything that would fail the vertical line test would now fail a horizontal line test, okay? So if the original function has two values on the same y, in other words, a horizontal line cuts through it twice, you know it's not one-to-one, okay?
Let's say so.
Yes?
So trig function doesn't have an inverse function.
Well, exactly. Trig functions as a whole do not have inverse functions. Now, we talk about inverse sine, inverse cosine, inverse tangent.
But it means something else.
But, well, it doesn't mean something else, but it means that we have limited the domain. Okay? That's why when we did inverse sine, the domain for inverse sine was negative pi over 2 to pi over 2. And for cosine, the domain was 0 to pi. And the tangent, the domain is negative pi over 2 to pi over 2. Okay? So for those, we were able to make an inverse function within a limited domain, and then we were able to use coterminal angles to get other possibilities. Okay? But notice that's why your calculator, when you hit inverse sine, only gives you one answer. But then you have to use reference angles and coterminal angles to get other possible answers to an equation. Okay? So, good question though. The trig functions by themselves would not have inverses, but we limit the domain and the range there so that it does. Okay? So if we're trying to find an inverse function, okay, first of all, determine if it has one. Okay? Then solve for x as a function of y and interchange the x and the y. The resulting equation is the inverse. Okay? Then define the domain of the inverse to be the range of f, and then verify that it actually works. Okay? So, if I'm finding the inverse function here, okay, I have y equals the square root of 2x minus 3. So following this method here, I ask myself, does this actually have an inverse? And because I know the parent function, I know that this is the radical function, but it's been shifted a little bit and it's been stretched, but I know the general shape looks like this. And that's going to be 1-to-1. I know the radical function is going to be a monotonic function. So I verified, at least mentally, that it is going to have an inverse. And now what I do is I start solving it. So I make this y squared equals 2x minus 3. I add 3, y squared plus 3 is 2x. So x is y squared plus 3 over 2. That means f inverse, keep writing prime, f inverse of x is, notice here I'm swapping the x and the y, so it's going to be x squared plus 3 over 2. Okay? So that's my inverse function.
Do you have to do the other steps or no?
Well, let's look at this here, okay? The domain and the range. What is the range of the radical function if it hasn't been shifted up or down?
Greater than 0.
Greater than or equal to 0, okay? So f, I'll use y y is greater than or equal to 0. Okay? The domain here is what?
2x minus 3 greater than 0. Greater than or equal to 0.
Yeah, there you go. 2x minus 3 is greater than or equal to 0. So that means x has to be greater than or equal to 3 halves, right? Good. So now we look at this function and we say, okay, well, what is our domain? What is our domain here for what x can be? Well, what would you say?
For the inverse function,
For the inverse function,
then
our domain would have to be what?
x is greater than or equal to 0.
X is greater than or equal to 0. Okay? X has to be greater than or equal to 0. And that means the range then, if the smallest x can be a 0, if I plug in a 0, what do I get? I get 3 halves. Okay? So the y is going to be greater than or equal to 3 halves. Okay? Finally here, we can go ahead and do 5. Verify that the square root of 2 times x squared plus 3 over 2 minus 3 equals x. And you would also show that radical 2x minus 3 squared plus 3 all over 2 equals x. I'm not going to show all the work for now. You guys can do the algebra, but you would show the work. Don't just say that. If you're told to prove it, show the work. Okay? All right. I wanted to look at this last one here. Show that the sine function is not 1-to-1 on the real line. Well, a very simple one. Okay, if we just sketch this, you guys know the sine function starts at 1, it goes down to -1. Here it is at 2 pi. Here's pi. Okay, if I extend this, here's a -2 pi. Oh, sheesh. Can't get this quite right. Get that half. Get that half. That's about as good as I'm going to get. Okay, so we've got that. Obviously, we can see that it is not 1-to-1 because right here, even, you could see it's not 1-to-1. Okay? Now, the second part says, show that -pi/2 to pi/2 is the largest interval centered at the origin, for which f is strictly monotonic. So if I go to the right, I go to the max, okay, and that exists at pi/2, okay? Once I hit the max, it's going to start coming down, and now I've failed the horizontal line test, okay? So I've got from 0 over to pi/2. Same thing over here, if I go down to the min, if I kept going, it's still going to start going up, and now I failed the horizontal line test again. Where does that min occur? It occurs at -pi/2. So there we have the largest interval centered at the origin where f is strictly monotonic. Okay? Now you can also say then, find the value of its derivative. I know where the max or min are because we know what the function is. Okay? If we had to prove this somehow, we would go ahead and say f prime is cosine, and cosine equals 0 when x is negative pi over 2, pi over 2, and so on. Okay? And then we could show a whole sine diagram. Okay? Negative pi over 2, pi over 2. And we see it's increasing, it's positive, negative over here, okay? So that's going to be our monotonic interval, okay?